conference will now be recorded.
Yeah, very good morning to everyone. So in the last session, we started with very good data flow modeling technique for combination logic circuit, correct? You remember we did for 1 bit full adder, 4 bit full adder, subtractor, 1 bit full subtractor, and then magnitude comparator, and then carry look ahead adder we did in the last session. And what other programs we have done on combinational. Like you can think of how to do MSI circuits like multiplexers, demultiplexer. Correct, multiplexer we have done one question. 4x1 multiplexer using logic gates, also using conditional operator, means ternary operator. Correct. You try to do other various configurations of the multiplexer, 8x1. You should know logic, how to do the data flow modeling technique for the MSI circuits, like multiplexer, demultiplexer, encoders, decoders, comparator we have done, one magnitude comparator we have done. So you look at any logical equation, you can able to write a data flow modeling technique. Correct. So now today we'll start with a few examples on sequential logic circuits. You know what is mean by sequential logic circuits, right? Where output is depending on the present state as well as the previous state. The previous state will be preserved in the history, means stored in the memory. So in digital vocabulary, memory is nothing but what? How to build a basic storage element is that latch and flip-flops. Latch and flip-flops are used to store the 1-bit data. Correct. So by combining group of flip-flops together, that forms a register. Now you can store 4-bit, 8-bit, so on. Now let us start with questions on sequential logic circuit. See, anybody done the program for this? Okay, can you tell me what is the program for the negative edge triggering D flip-flop? What is negative edge triggering D flip-flop? So this is a negative edge triggering D flip-flop, right? So let us copy this. This is the one negative edge triggering D flip-flop. So how to model this using data flow modeling technique? Can you tell me what is the program to this? Look at this circuit diagram. What is C bar is equal to what? C bar is equal to not of clear. Correct. What is S is equal to? S is nothing but R bar. Correct. R bar. What operation then? This is an AND operation, means first I need to do AND. And what is another input is nothing but yes. So this is AND operation I am doing. How to do the NAND? Complement this using fiddle symbol. Then what is this? S is equal to? S bar. AND operation, correct. Again, C bar or C bar, okay. C bar is nothing but what? Not up clear. Not up clear. So this is a not gate here, correct. Second this is nothing but C bar. And what is one more input is nothing but not up clock. How to read the not up clock? Not up CLK. Again, this is nothing but what? Not operation. So what about R? R is nothing but yes, AND operation of not of clock. Again, AND operation of R bar. R bar is nothing but what? Not. What about R bar is? R bar is nothing but R AND operation of C bar, correct. Again, AND operation of D. Again, this is nothing but what? NAND operation. What is Q is? Q is nothing but yes AND of Q bar. Q bar, again this is nothing but what? NAND operation. What about Q bar is? Q, this is nothing but Q, C bar and R. Again this is nothing but NAND. So these are the logical equation for what is this is nothing but negative edge. Negative edge triggering what flip flop it is? D flip flop. Now can you write a program to this quickly? Is the program? So what are the inputs to this is nothing but clear? Clock, D, Q, Q bar. What are the wire data types are? C bar, S bar, S, R and R bar. Now write a program to this. So I need to start with what? Module. Module name. Shall I take the module name is D flip flop? What are the inputs are? Clear? Let us go with like this. Clock, clear, D, Q, Q bar are the inputs and outputs. This is a port list. Now what is the next step? Port declaration. Inputs are clock, clear and D. Then output are Q and Q bar. Q and Q bar. Next is wire. What are the wires are? C bar. Is it clock is a wire? S bar. S, R, R bar. R bar. These are the wire type. Next what I need to do? Assign. So we are doing data flow modeling technique. Assign. Correct. What I need to assign? First C bar. Correct. C bar is equal to what? Not of. Correct. Not of clear. I am doing this. Are you understand? Coming to this circuit. First I am doing this. C bar is equal to what? Clear bar. Next is S bar. What is S bar is? Not of R bar and of S. Correct. So now you should quickly tell me this is assign what? S bar is equal to what? Not of not of R bar and S. Next assign assign yes, correct. What is S is? What is S is? S is nothing but S bar and C bar, not of clock. S bar, correct. This is S bar, then C bar and not of clock. Not of clock. Correct. Next R. What is R is? What is R? R is S into not of clock into R bar. Can you tell me this? S into, correct? S into not of R bar and not of R bar. Okay. This is not of R bar. Is it correct? S into R bar into not of clock. S into R bar into not of clock. Not of clock. Next. So R bar, correct? What is R bar is? D into, correct. R bar is nothing but R into C bar into D. So R into, correct. R and R, C bar, this is C bar, correct? C bar into D. Now I need to write it for what? Q. What is Q is? S and Q bar. S and Q bar. Then what is Q bar is C bar into Q and R. C bar into Q and R. Now, in the what? Let us remove this lines. Now, this is our design file. Let us run it for what? Syntax error. So, no syntax error to this. So, now we are modeled the what? What we are modeling here? D flip-flop. What D flip-flop it is? It is a data flow model of negative edge D flip-flop. Negative edge D flip-flop. Correct? Now, can you write the test bench to this? What are the inputs are these? Clock is a one input. D is a one input. Clear is a one input. Q1, Q bar are the outputs. Correct. So, how negative edge technique flip-flop will works? How negative edge technique D flip-flop works? Whenever negative edge comes, right? If D is equal to 0, Q is equal to 0, that Q remains same until the next negative edge comes. Correct? Then that is depending upon the clear. When clear is high, always Q is equal to 0. Only this will work as a D flip-flop when clear is equal to what? 0. Since you are using Q bar here, right? You can see here Q bar, C bar, clear bar. This is nothing but. So when clear is high, Q always is equal to 0. Q is equal to 0. When clear is equal to low, then this is working as a what? D flip-flop. This should work as a D flip-flop. Did you understand? Now for this, how to write the test bench to this, to check this operation of the D flip-flop? What you need to write the test bench to this? I need to initialize the clock, correct, clock generation. Then what you need? Clear and the D. Then you monitor and then you finish. Then you print the output. Correct. So let us write the test bench to this module. Module name I am going to take it as TB. Here what are the reg type? Clock, clear, D. Then wire data type are Q and Q bar. Q and Q bar. Now what I need to do after this? I need to instantiate the design. Then this is design under the UT, design under the test. So let me go with port connection by name. Okay, port connection by name. So this is nothing but dot of what? Clock of what? Clock. Correct. Again dot clear of clear. Again dot D of D. Then dot Q of Q. Then dot Q bar of Q bar. So I have done with port declaration. Let me write the end module. Yes. So this is my test bench name TB, and then this is my end module. Now I have instantiated the design. Now what I need to do? Sequential. So first we need to generate the clock, right? Generation of the clock. Generation of the clock. How to generate the clock? What are the different way you can generate the clock? So you can generate the clock using forever into the initial block. That should be inside the initial block. Okay, forever loop is nothing but it is an infinite loop. This keep continuing. Or you can use the always block. Always block also continuous execution. Okay, where your initial begin is one-time execution, where always block will be continuously executed, like a loop. Okay, so I'll be using always block to generation of the clock. Always, then I'm going to give the period. What is this period? Means as time means It is a time period. How much I should make T on? How much I should make T on? Did you understand? So clock is equal to not of the clock. Not of the clock. This done with the generation of the clock. Single line. Because I am writing this complete in the single line. Therefore, this always block does not require a begin and end. Are you understand? How this will be generating the clock is, this is generating the this always statement will generate the clock like this. Where what is the T on is nothing but total time period. This is a TP, right? This is a TP, total time period. What is this is nothing but T on. What is this is nothing but T on. Where T on is equal to, it takes 5 unit, time unit. So this will take 5 nanosecond. And T off will take what? 5 nanosecond. Then what is the total time period is nothing but 10 nanoseconds. So this always, whatever always, I'm using a hash 5. So this will create a clock of the time period of how much? 10 nanoseconds. If I'm giving like this, 10, time period of 20. Did you understand? Or I can write like this also. What I'm going to do, I'm going to write the parameter. So let us write TP. TP is equal to 10. TP is equal to 10. Here what I'm going to do, instead of writing 10, I'm going to write like this. TP divided by 2. This is also fine. I'm declaring the what? Parameter. Constant. What is TP value is? 10. Now what I'm doing is, 10 divided by 2 means what? 5. So what is the time period of this is? Total time period is nothing but 10. So by simply varying of this, I can create a different time period of the clock. If I'm giving 5, what is time period is? 5. 5 divided by 2 means how much? 2.5. T on should be 2.5 and T off should be 2.5. If I'm giving the parameter TP is equal to 20, what time period I'm going to give? Time period is 20, T on should be 10 and T off should be 10. Did you understand? So by varying this, I can make the different time period of the clock. Okay. Let us remove this for now. Now I'm going to make this is the time of what? 10. Time period of 10. I've generated the clock. Because I need a clock, right? Clock to work with what? D flip flop. Then what I need to do? Okay, let us do one thing. I'm going to use the initial dollar symbol monitor. Dollar symbol monitor. So what I'm going to monitor is nothing but let us monitor the time. How to monitor the time? Current simulation time. How you get this nothing but using system task function dollar symbol time. Now I'm going to write what? Clock. I want to monitor the clock. Let us print the clock. Okay. Then what I want to see? Clear? Clear is the one input. Let me print the monitor the clear. Then what I need to monitor? T percentage P. Then what I want to monitor? Q. Q is equal to percentage B. Then top space Q bar. Q bar is equal to percentage B. Now what argument I need to pass? Clock. Clear. T. Q. Q bar. So I'm putting this in the only one statement. Is that my initial requires begin and end? Correct? I can write the initial begin right like this also, right? Writing a single statement so that I'm not grouping with what? Begin and end. Okay, what is next step? Clock is here. I'm just observing the clock. I'm generating the clock, right? If you not mention also, no problem. This is for just seeing the output. I want to see whenever my negative edges come, what is my Q output? What is my Q output whenever the rising edge and falling edge? That's why I'm printing the clock also. Yeah. So instead of this is a clock generation. You're talking about clock generation, or you want to see the output whenever the negative comes or positive comes? See, this question is negative edge triggering flip flop. Okay, I am printing the clock here. So what is a negative means? Whenever the transition takes from where to where, 1 to 0. If my clock will take the transition, so this is a positive edge. This we call it as positive edge. Correct? Positive edge. This will take a transition from where to where? 0 to 1. Whenever my clocks are changing from what? 1 to 0, this is nothing but what? My negative edge. My negative edge. So this whatever I am using here always /5. That clock is equal to not of clock. This is generating the clock like this. You understand? So with the clock time period should be how much it is. T on should be 5. This one statement. So this is 5 and this is 5. The total time period is nothing but 10. This is my positive edge and this is my negative edge. Did you understand? When the transition takes from 0 to 1 is positive, 1 to 0 means negative edge. So I'm printing the clock here. I'm monitoring the clock here. Whenever clock changes from 1 to 0, that gives me what edge? Negative edge. Whenever clock changing from 0 to 1, that means what? Positive edge. So here this is my clock generation. But how this D flip-flop, you are writing the code here above, you are writing the code above here, how this D flip-flop will work? This D flip-flop is for what? Negative edge triggering flip-flop. Whenever negative comes, output changes, it will remain same until the what? Next negative comes. This behavior we are modeling here. Did you understand? Are you clear? Let me draw the timing diagram to this also. So this is my clock. Let us take clock is changing with respect to the time. So these are the negative edges, right? Let us write these are negative edge, negative edge, negative edge, negative edge. These are negative edge. This is my clock. So I am using one more input is nothing but what? Clear. So if my clear is I, and up to this speed, let us make this up to this speed is I, then I am going to make this is low. This is low. These are my negative edges. So let me draw it. These are negative edge. These are negative edge. These are negative edge. These are negative edge. Negative edge. Negative edge. These are negative edge. Let me draw the D input. Then let me draw the Q1, Q bar. Q1, Q bar. So this is T. Let us take the arbitrary D input. So this is the D. Let us make arbitrary D input like this. Just writing the arbitrary D input. Now what is Q and Q bar? What is Q and Q bar? So when my clear is I, Q is equal to 0. We are making Q is what? 0. This is working like when clear is I, it is making what? Q is equal to 0. When clear is 0, what is the input at this negative edge comes? 1. D is 1 now. Correct. Now what is D flip-flop means? Output following the input. Now output becomes what? 1. It will remain same until the what? Next negative comes. This is the next negative. Did you understand? Now coming to this negate, what is my clear is 0. What is my D is 1. It will stay remain same what? Until the next negate comes. Now coming to this, what is my clear is 0. What is my D is 0. Now this changes to what? 0. It will stay remain same until the what? Next negate comes. Again here 0. 0 means what? 0. Again here this is clear is 0. Now what is D is 1. Now D remains 1 until the what? Next negate comes. So this is a D flip flop. Now Q bar is nothing but what? Complement of this. Correct? This is what we are modeling using negative edge technique D flip. For that what I need? Clock. Then what I need? Clear. What I need? D. Then I should see what is the output of Q and Q bar. Now let us write the program to this. Okay. Now what I need first is I'm monitoring. I'm monitoring the what value? Clock, clear, D, then Q, Q bar. So these are the arguments I'm passing to this. Now what is this is nothing but? This is nothing but? Let us remove this here to here. What is this always /5 clock is equal to not on clock? It is going to generating the clock with the time period of how much? 10 nanoseconds. This is what? Monitoring. Monitoring the inputs and outputs. Input and outputs. Did you understand? Is it clear this 2 lines of program? Now what I need to do next step? I should do initial begin, correct. Now initially I am going to make clock is equal to 0. Okay. Let us make clear is equal to 1. Clear is equal to 1 and D is equal to 0. So this will start executing at what time? At the 0 simulation time. So at the 0 simulation time, what is my clock? I'm initializing clock to what? 0. And then clear to 1. And D also I'm giving. I should see what is the out. Okay. Now what I'm going to do, let me give after 15 times time. Now here what I'm going to do, let us make clear is equal to 0. D is equal to 1. D is equal to 1 I am giving. Then again after let us make 35 slash 35. 35. Again what I am going to do is clear is equal to 0. Or you can make D is equal to 0 means already clear is 0. Already clear is 0. Now I am making what? D is equal to 0. Now let me give some timestamp 55. Now here what I am going to do, I will be making clear is equal to 1. Clear is equal to 1. So what is my D is 0. Previously D is equal to 0 is there. Did you understand this? So now I initialize here. Then what I am going to do, end this one. So this is total, this initial block I am taking for what? Initialization of the clock, initialization of the clear, and initialization of the D value. Are you understanding? Now in the one more initial block, one more initial begin. Let me finish this. Let me finish at the 100. Okay. Dollar symbol finish. Dollar symbol finish. Then end. Then end the one. End the one. Did you understand this? Now let us run for the syntax error. Then we will observe the output. So there are line number 61. There are 2 end modules are there. Let us remove this. You can run the program. Just copy and restart this. Take some other online compiler. Let's copy the same here. This is the output I'm getting for this. Okay. So I think now from here you can't able to exactly understand how this works as a D flip-flop. So what I'm going to do, let me copy this program and let me run in the models. We'll observe the timing diagram. Then you will be understand. Okay. So let us copy the test design file first. Let me make the directives. D flip-flop. So what I need to write here? First we need to write the design file, right? So let us copy this design file. This is a design file. So what extension I need to say this is? So let us make d flip-flop dot v, and then this I need to change it to what? All file, save this. Now I have saved the d flip-flop design file. Now what I need to do? I need to copy the test bench. So let us copy the test bench. So let me save this as what? tb.v extension and all file format. Let us save. Now I have done the design file and the test bench. Now what I need to do? Run.do file. So let us copy some from the other file. Run.do file. Let me copy. This is the same, right? What is the file name I have given is tb.v, and this tb under design under test. Let us file, save as. What I want to do? Run.do file. What extension it is? .do extension. Now let us save this. Now I have done with what? So we have done with d flip-flop, design file, test bench, run.do file. Let us remove this. Now let me invoke the models. So this is a command I am doing. Model C space -do run.do run this. So it is done with, and there is error here, loading in macro. What is the error? Can you identify this error?
The include statement. The include statement. Macro.
We should include what? In my TB, I have not included with what? My design file. So insert mode, tick include, correct? What I need to include? What is file name I have given is d flip-flop dot.
Yes.
How to save all is nothing but :wr. Okay. You can write us on this program. So this is the output. I'm monitoring, since I'm using $12 monitor, it prints the output here. Okay. So at the clock 0, clock 5, clock 10, because I'm giving the time period of how much? T on should be 5. So 5, 10, 15, 20, 25, so on. Clear? So from where to where I'm making the clear? At the up to 10, you can see my program. Let us open the design file. Sorry, test bench. This is my test bench. You can see at a time t0, correct? At a time t0, what I am doing? Clock is equal to 0, clear is equal to 1, d is equal to 0. Up to timestamp of 15, correct? 5 plus 10 means up to 15. My clear is equal to what? 1. You to understand? This is 0 timestamp. This is 5. This is 10. Up to here it is what? Clear is equal to 1. Then d is equal to q is equal to 0 only. Correct? Now coming to our time 15. What is my clear is nothing but? I am making clear is equal to 0. What is d is equal to? 1. D is equal to 1. But this changes is happening at what? Negative edge. The transition takes from where to where? 1 to 0 means what? Negative edge. Okay. Let me explain the timing diagram, then you will be understanding. Okay. So this is the timing diagram. This is my clock. Okay. So you can ignore here. What you can ignore is nothing but C bar, S bar, SR and Q bar. So these are Y data type. For understanding of this timing diagram, for the moment you ignore this. Later you can understand what is the Q, S, R, C, R bar and R bar, S bar and C bar. Now this is my clock. So this is my negative edge. Correct? This is my negative edge. This is my negative edge. This is my negative edge, so on. Correct? What is this? Is nothing but clear. Clear is made up to what time period? Up to here my clear is what? 1. Correct? You can see this is 1, right? This is I. I means what? 1. So D also I am making what? 0. Clear is 1 and D is 0. What is Q is equal to? When clear is I means Q is equal to 0, Q bar is equal to 1. So whenever next negative edge comes here, because we are designing what? Negative edge triggering flip-flop. Whenever next negative edge comes, what is my clear is? 0. What is my D is? 1. Now what is a D flip-flop is? Output follows the input. Now Q is also D. You can see Q is also, sir. Q is 1. It will stay remain same what? Until the next negative edge comes. Correct? What is my clear is? Clear. Clear is 0. What is D is? What is Q is? 1. Output follows the input. It will stay remain same until what? Next negative edge comes. What is my clear is? What is Q is? 1. What is what D is 1. Q is equal to 1. It will stay remain same what? Until the next negative edge comes. So what is clear is 0. So this will be there until the what? This I should be there until the next negative edge comes. Whenever here clear is 0, D is equal to 0, this is 0 until the next negative edge. Now this is working as a negative edge triggering D flip-flop. Did you understand? Same thing I have printed in the transcript here. I am monitoring at the clock 0 what is my Q, at the clock 5 what is my Q, at the clock 10 what is my Q. This is what I am monitoring. Are you understand this program? First you should understand that how to write the test bench to this. Correct? So this is for what? If I am not using this, what will happen? If I am commenting this line, it's not going to print the what? Clock. This data will not printing it in the console or a transcript. Correct? Here in the my run.do file, I am adding the what? Adding the wave, so that I can able to see the what? Waveform here. All the inputs and output waveforms here. You understand? What is this line for? This line for what? Clock generation. I am generating the clock. Then this initial block for what? Initializing the clock beginning, and then what is my clear pin? What is my D input? Then I am giving a different timestamp here. Did you understand? So then I am ending this. This is for initialization. Let me write it here. This is for what? Initialization. Okay. Initialization of the inputs. Then in one more initial block, what I am doing, because how this will be executed in the Verilog, all these blocks, whatever, how many initial blocks, 1, 2, 3 initial blocks I am using, one always block I am using, correct? How this will be executed? How all these initial blocks will be executed in Verilog? Verilog supports for what? Concurrent execution. So this initial block, this initial blocks, this always block, this initial block, this initial blocks will start executing at what time? T is equal to 0, and end is depending upon how many statements we are using in the initial begin or always begin statements. But all are concurrently executing. Okay, now another initial begin, what I am doing? I am finishing the simulation. Then I am ending this. How to understand this program? Negative edge triggering D flip-flop using what model it is? Data flow modeling technique. You can do this within 1 or 2 lines of code in behavioral model using always block. We'll see that later. How to model the D flip-flop using behavioral model. Since we are working on now, as of now, data flow modeling. So if I give this D flip-flop, negative edge triggering D flip-flop, how to model the negative edge triggering D flip-flop. Is it clear? Now what is my question I was asking about? Coming to my question. So write a program of data flow modeling of what? Negative edge triggering D flip-flop. Correct. So this is my, let me copy this to here. What is this file is? My design file. Okay. Let us copy the test bench. This is my test bench. Did you understand this? Now what is my question is, next question is, so write a program. Is it first you tell me, did you understand this program? Did you understand this program? How to write the design file using data flow modeling technique. Then how to write the what? Test bench to this. Do you have any questions here? I'm using this timestamp. It is a timing diagram. Okay. Okay, what is your question here now? How it works then? Okay. Let me explain it. This is my test bench. Okay. So this will execute at what time? T is equal to 0. Correct. So at the T is equal to 0 means this is a timestamp. This is a timestamp and T is equal to 0. Correct. Now when my clear changes to 0, after this time 15, you can see this is at 5. This is up to here it is 5. Again it is 10. Again it is what? 15. At 15 what happens here? My clear goes to what? 0. Before that what I am making? Clear is equal to 1. And D also I am making what? 0. D also I am making 0. When clear is 1, this flip-flop works, Q becomes 0 and Q bar is 1. Did you understand? At the time 15 my clear goes what? 0. What I am making here? D is equal to 1. This is a negative edge triggering flip-flop. This will respond only when negate comes. But I made these changes at what? Raising edge. But we are designing what flip-flop? Negative edge. So at this negative edge, it's check the clear. It check the what? D. Now it's changing the output. D flip-flop, how it works? Output follows the input. Negative edge means whenever negative edge comes, based upon the clear and D, it changes. It will stay remain same what? Until the next negative edge comes. So I made clear is equal to 0, D is equal to 1 at the 15. At what time again I am making clear is equal to, after up to 35 I am making what? D is equal to 1. After 35 what I am doing is D is equal to 0. Means this is 35 plus 15. 35 15 means what? 50. At 50 D becomes what? 0. Again at where I am changing clear to 1. 55. You can see up to 50. Let us see up to 50. My clear D is what 1. Up to 50, what I'm doing? D is equal to 0, and this will be there. D is 0. I'm making continuously. So where I'm changing my clear to 1. So clear to 1. Okay, let us see this. The clear is not changing. This is D changing here. This is my clear. So when clear is 0, D flip flop, D follows the Q. It is following here, it is following here, it is following here, again it is following here. Let us see this at the clear. I'm making a clear is equal to 1. When clear is equal to 1, what it should be? Q. Q should be 0. It should not follows Q follows the D when Q is equal to 1. Q follows the D only when Q is equal to what? Sorry, clear is equal to what? 0. So here I'm making, after this timestamp, I'm making the clear is equal to 1. So let us save again this program and compile this again. Let me clarify this now. My clear is not changing, but in my design test bench, after 35, hmm, 15 plus, correct. It is not changing at what? 55, because it is sequentially executing. You are correct. So this is at the start at what time? 15. So 15 plus 35. 50. Again 50 plus 55. 105. So let me do one thing. I am going to change at the 5. Now this will at what time it should change? At 55. This should change at the 55. Good. You have noticed the good point. Now let us see here. At 55, clear becomes 1. When clear is equal to 1, what is my Q is equal to? 0, 1. Let us check the timing diagram to this. So at the 55, we are making what? Q, clear is equal to 1. When clear is equal to 1, if D is equal to 0 or 1, what is Q is nothing but 0 only. Are you understand this? So previous case, what happens at 105, it is changing clear to 1 in previous case. Correct? But I am finishing at what time? 100 time. Is it clear? Now this is how the D flip flop works. Negative triggering D flip flop. Okay. Now what is my question is here? My question is here. I need to design the what? Counter. What counter? Asynchronous counter. This is my question. First, what I need to do, using this negative triggering D flip flop, you model this negative triggering D flip flop using data flow modeling. Then what you have to do, use this D flip flop to design the what? T flip flop. How to get the T flip flop from the D flip flop? So by complementing the Q output, so this will work as a T flip flop, toggling flip flop. Did you understand? Use this toggling flip flop to model the what? 4-bit ripple count. Now what I am doing here is that I am writing the data flow model for the negative triggering D flip flop, and also I am writing the test bench. I am showing you that this is how D flip flop works. Now use this to model the what? T flip flop. Write the test bench and see how it is working as toggling output. Then use this to model the what? 4-bit ripple counter. Now we have done this. Negative triggering D flip flop. Now can you write a program to this by instantiating the D flip flop? So can you write a program to this? How to write a program to this one? Let us copy this. What are the inputs and outputs to this? Inputs are clock and reset. Output is only Q. Correct. Now, we understand it how to model this. Just now we understand this. Correct. Now use this, instantiate this D flip-flop to model the what? T flip-flop. How to model this? Okay, let us talk about this question. Let us come to this. This is the program, correct? This is a working program. Let me copy this sign. Working program. Yeah. Now one small changes we have done is what? 5. Correct. Clear we are making at 155. Now coming to this is my D flip-flop. Negative is taking D flip-flop. Now I should instantiate this to model the what? T flip-flop. How to do this? So okay, let me keep this aside. Okay, test bench I'll be using same thing for T flip-flop also. Now this is my what? D flip-flop. Now I'm going to use one more module. Module, correct? Module. Shall I write the module name is TB? What are the inputs and outputs to this? Clock is the input, correct? Reset. Reset is the input, then Q is the output. Correct? Now what are the inputs here? Inputs are, these inputs are what? Clock and reset. Clock and reset. Output is Q. Did you understand? Now how to model the T flip-flop? How to model the T flip-flop? Use this. We need to instantiate the what? D flip-flop, correct? Instantiate the D flip-flop. So this is DUT. Then what I need to do? You can see this diagram. Now I'm instantiating the D flip-flop. What is the input to this? Is nothing. D flip-flop. For D, what is the input is?
Q bar.
Q bar. Right? D is nothing but it is Q bar. Means not of Q. Correct? And then what is the output of this T flip-flop is? Q. Correct? Q is the output. Then inputs is nothing but what? Output is Q, inputs are not of Q, and then clock and reset. So this is my D flip-flop. Now we have modeled this one, D flip-flop. This is a D flip-flop, what we have modeled. S, R bar, S bar, correct? Using the data flow modeling technique. Negative technique D flip-flop. Now we need to model the what? We need to model the T flip-flop. So let me show you that the code for the T flip-flop. So here, sorry, not this one. This is the one T flip-flop. Now module name is TP. What are the outputs are? Input and output are Q, clock and the clear. So reset, or you can use the clear also, no problem. Reset and clear Both make same sense here. Now what I am doing, input is clock and clear. So what we are instantiating the what? H degree D flip flop. How we are instantiating this? So complement of the Q is feeding to feedback, and notice Q bar is not needed when you are working with what? H degree ripple count. Q bar is not necessary. But when you are modeling the D flip flop, you are modeling the output Q and Q bar both. Correct. Here Q bar is not necessary. So now I am instantiating the what? What is this? Is nothing but H degree D flip flop. D flip flop on what is the output is? Q. What is the input is? Not of Q. What is the one more input is? Clock and the clear. That is what I am doing here. So this is D flip flop. This is my D flip flop name. I am instantiating this D flip flop. Then what are the inputs to this? Is nothing but what is the output is Q. Then what is the input to D flip flop means? Not of Q. Not of Q. Correct? Then clock. Then okay, let me use the clear here also. No problem. Reset and clear makes same sense. I am going to change this what? Reset to the clear. Here also I am making this into what? Clear. Let us change in this circuit. So this I am going to change into what? Clear. Did you understand? Now this is my T flip flop. Then end this. Then what I need to do? In the module. By instantiating the D flip flop, I have modeled the what? T flip flop. How means Q is complemented and that is feeding to what? Your D. So in T flip flop, Q is the output, correct? What are the input is nothing but not of Q, clock and the clear. So let me comment these lines first, test bench. Then I am going to run this T flip flop. So this is T flip flop. What T flip flop it is? Negative edge or positive edge? Negative edge degree T flip flop. This is, let me write, negative edge triggering T flip flop. Are you understand? Now let us check for the syntax errors. There is a line number 24. So wrong number of ports expecting 5 got 4. So 1, 2, 3 is there. So this T flip flop, D flip flop, Q, clock, clear and Q. These are the inputs. Okay, let us check this. Clock, clear, D, Q and Q bar. And this is D flip flop, DUT, Q, not of Q. There are 3 inputs I am using. One is clock, one is clear, one is not of Q, then again this is Q. So wrong number of ports expecting 5 and got 4.
D flip flop has Q bar port.
So why I need to declare it?
Right.
Why? D flip flop. Okay. Is it any wire I have using here? Oh, this is the input. This is output. This is output.
That's the
Not of Q is input. Clock is a one input. Clear is a one input.
the output,
Not of Q?
Q bar output from the flip flop is missing.
Okay. This I need to write what? Q. There's a mistake here. This is 3 inputs I'm using.
The DUT should have 5 ports.
So this is clock 1, 2, 3, 4, 5. But I'm not using Q bar here. Not using the Q bar. So Q bar is not necessary for me. I am observing what? Q. This is what I said. Instantiating the H triggering D flip flop. Okay. So complement output of Q is feedback, and notice of Q bar is not needed. So what I need to do in this case is nothing but I need to do unconnected port, one port. How to do the unconnected port? By giving the space. Correct? Correct. Now it will be how many ports now? It is 5 ports. So now what I want is Q bar is unconnected. How to unconnect it? We saw about regarding the port connection, right? How to drop unconnected ports. Now this is my T flip flop. Negative H triggering T flip. Are you understand? Now can you write a test bench to this? To understand this? What is the test bench to this? Is nothing. Let us pull up this program up. So write a test bench to this. Module TB, clock, clear. What are the inputs and outputs to this? See about this one. Clock and clear. And the Q is the output. Correct. Now I am not using what? Q bars. Let me remove this Q bar. Then what I need to do? I need to instantiate what? D flip flop or T flip flop? Toggling flip flop. T flip flop. I need to instantiate. Then this is connecting into what? Clock according to the port. This is a clock. Clear. Then I am going to remove this. D. Correct. D is not there. I will be removing this. And Q bar is also not there. I will be removing the one. Q bar. Now this port connection by name is correct now. According to this port list, clock, clear and the Q. Next what I need to do? I need to monitor the clock, clear, and D is not required. Let me remove the D. Correct. D is not required. Let me remove the D. And Q bar is also not required. Let me remove the Q bar. Let me give the tab space here. Then here I need to remove what? D and then Q bar. Correct. Now this is what? Clock generation. This is a clock generation. And here, this is a clock. Clear. D is not there. Let us remove the D. Again, here also I am going to remove the D. Let us remove the D up to here. Now let us see that whether it is working as a T flip flop. Correct. Now this is for what? Initialization of the clock and the clear. If one clock cycle, if it is 0, Q is 0, next clock cycle what it should happen? 1 means toggling it should happen. Toggling it should happen. Then I'm finishing the simulation at once, 100. Okay. Now let us run this. Okay. You can say this is a clock 0. What is my clear is 1. So it is taking whenever the clear is equal to 1. Okay. For all this, it is taking what? Clear is equal to 1 now. The way I have initialized is not correct. Can you rewrite this program? Okay, what happens in this case is nothing but Q is taking what? Z. Means high impedance state. Since we are declaring Q as a what? Y data type, by default it is taking what? Z. It is not working as a toggling flip flop. So here, up to this 15, we are making what? Clear is equal to 1. Clear is working fine. And then clear, we are making 0 up to what? Clock cycle. So up to here. So this is nothing but what? 50. Up to 50, clear is equal to 0. At 50, we are making what? Clear is equal to 1. Did you understand? Now, but Q I am getting what? High impedance Z only. It is not working as a toggling operation. Can you see what changes I have to do in this program? What changes I need to do? Now here clock and clear is working fine, but Q is giving the high impedance state.
Sir, please check D flip-flop instantiation, sir.
D flip flop, okay. This is my D
In
flip
a
flop.
given instantiation, Q as the output, but in D flip-flop we take as a starting as a clock, sir. Order is not correct, sir. You're giving output post.
No, whenever I'm instantiating this is nothing but like a primitive gate instantiation, right? This is a D flip flop. This is a D flip flop duty name. Then I'm connecting the outputs first. First output port connection, then followed by what? Input port connection. This is correct.
No, sir, it's different in the definition. The order is different.
Your voice is not proper. Can you repeat again?
The D flip flop, the order of the ports, it's different.
There's a clock clear DA and Q and
Yes.
Q bar and
It's
G.
natural.
Okay. Okay, you're talking about first you write the D
Yes, sir.
outputs. First output, then clock clear under D. This is not a matter. Okay, this is taking as, it is not taking, I'm doing the port connection. First outputs, then followed by the inputs. So first outputs followed by the inputs. But
Sir,
talking
D
is not
you
happening.
can place as third base. Put the D as third base.
Okay, this is a D,
Yeah.
then clock, then the clear. Now I'm connected here. Okay. Here D is nothing but connecting to what? Q bar. Then clock and clear. Okay. Yeah, now this is working as toggling. Yeah. Now the problem mistake what I have done here is port connections was not correct. So here when I'm instantiating the D flip flop, these two are output ports, followed by what? Input port. Now here earlier what I did, first I did the clock, clear, D and Q bar. Now the way I am initializing the port here, I am doing the same thing here. This Q bar, this is D, clock and then clear. Now here also I am doing Q bar, but Q bar I am doing which I don't need, so that I will drop the Q bar. Now what is D is connecting into? D is connecting into Q bar, correct? Now you can see this is a D. Now this D is connecting into what? Q bar, then clock connection, clock and clock, then clear and clear. Now this is a test bench I am writing for this. Did you understand this? Now at the clock 0, my clear is what? Up to whenever the clear is 1, my what is Q output will be? 0. Whenever it is changing, my clock is changing from 1 to 0 means negative edge. Whenever negative edge is there, since Q is equal to 0, it is toggling here. Q becomes 1. Again, it will stay remain same what? Until the next negative edge comes, 1 to 0. When next negative edge comes is nothing but here, this is 1 to 0, and next edge, negative edge comes where? Here, 1 to 0. Now Q is changing what? Again, it is toggling here. Are you understand? Let me do one thing. I am going to run this in the model sim, so we will see the timing time. Then you will be understand. Before that, you tell me, did you understand this? How to model the D flip flop? What mistake I have done? Here? Okay. Now let us copy this code. Let us make a folder. I'm going to remove this. What I want to do, D flip flop. Let us take, this is D flip flop, right? D flip flop. Let us copy the same design and test bench. So this is my design file for what? T flip-flop. Let me change this into T flip-flop. Just save this as T flip-flop.v. Save all the files. Now I am saving the T flip-flop. Now let us copy the test bench. Copy the test bench. So first line what I need to do? Tick include, right? Tick include. What is the file name I have given is T flip-flop dot. Let us save this. Save as. Let me save this as tv.v file. All files. This is my test bench. Now let us copy the same from the previous one. Here, my run.do file. This is a run.do file is same. The test bench file name as given is tb.v and name of the test bench is tb. The rest of things are same. Let us save as this. Save as run.do file and all file format saves. Now let us check for the files. So this is my T flip-flop. Okay, let us remove this. This is my design file for the T flip-flop. Correct. So this is actually here from year to year. Year to year it is what is this is nothing but negative edge triggering T flip-flop. Let us make this a T flip-flop whole. Okay. Now this is what? My T flip-flop. This is my design file. Let us save all. And this is my test bench. How do you understand? Now let us run this program. This is a T flip-flop. Okay. So I will be using the model sim -do run.do command. Now I'm done with the 0 errors. Is it I'm monitoring the output? Yes, I'm monitoring the output. Let us see. This is what monitoring. Dollar symbol monitor will print this one. Now odd wave is nothing but this will do. Now you can see here. This is my negative edge triggering T flip-flop. Only Q is there. Q bar is unconnected. Correct. So how this should work? T flip-flop. So whenever negative edge comes, so up to this timestamp 50, my clear is equal to what? 1. Since clear is 1, what is my Q is? 0. Whenever there is a negative edge comes here, my what is my clear is? 0. In previous case, my Q is what? 0 was there. Since clear is 0, this is a negative edge. Now toggle should happen here. Toggle happens here. This is 0 is there here. Now toggles to what? Once. This will stay remain same what? Until the next negative edge comes. At this negative edge, what is my clear is? 0. When clear is 0, next to negative edge comes, what it should happen? Toggling. Previous state is 1, now it is toggling to what? 0. Again this will be stay remain same until the what? Next to negative edge comes. Here again it is toggling is happen. Are you understand? Again whenever next to negative edge comes, at this point what is my clear is? I am making 1. When clear is 1, what will happen? Q remains what? 0. Q is toggling only when clear is equal to 0. Now this is my T flip-flop operation. Toggling operation. Using what? Negative edge triggering. T flip-flop. Using D flip-flop, we design the what? T flip-flop. Now our job is that use the T flip-flop now. Use the T flip-flop to model the what? Counter. What counter? 4-bit ripple count. Did you understand the flow of this program? Now let us copy these programs here. This is D flip-flop. Let us close this. Let's close this again. Let us open this file. This is a T flip-flop. This is my design file. Let us copy this. We are talking about this one, right? Write a program to data flow modeling of negative stringing D flip-flop. Use this to implement the what? T flip-flop. Now let us copy this test bench. Design file. And also I am going to copy the test bench. How do you understand this? Now what is the next program we need to do? Write a program of data flow modeling of 4-bit ripple counter. 4-bit ripple counter. How to design the 4-bit ripple counter? How 4-bit ripple counter will work? Let us close all this. How to model the 4-bit ripple counter? This is nothing but a 4-bit ripple counter, right? Let us write this. If I'm designing this using T flip-flop, this is my T flip-flop, 4-bit ripple counter. This is a negative edge of the clock, correct? So output of this is feeding input to this, right? Output of this is feeding what? Input to this. Output of this is feeding input to this. This is a T flip-flop, this is a clock, this is Q, this is TQ, this is TQ, this is TQ. So what I need to connect all these T flip-flops should be? This should be connecting into the one toggling operation. So this is the asynchronous counter or a ripple counter. Ripple counter, or we call this nothing but what? Asynchronous counter. Using what flip-flop? T flip-flop. So now we have modeled already T flip-flop we have modeled. Now we need to write a program for what? Ripple counter. So how many T flip-flop I need to instantiate? 4 T flip-flops, correct? 4 T flip-flop. Can you write a program to this? No? Can you model the ripple counter using T flip-flop? So up to here already we have done. Let us go to here. For the moment, I am going to comment this test bench. The test bench I am going to comment here. Let us pull down this here. Now this program is for what? Negative stringing D flip-flop. This program is for what? T flip-flop using what? T flip-flop. Now what I need to do is nothing but I need to model the what? We need to model the 4-bit ripple counter. So this is a 4-bit ripple counter. This is a T flip-flop. 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 Let us copy this here. So now what are the input to this? You can see. What are the inputs to this? Clock is the one input, correct? Clock is the input. Then this is the input. This is the input. This is the input. This is the output. This is the output. This is the output. This is the output. Now can you model this? Can you model this? What I need to start here? First, module, correct? Module. What is module name is? Ripple counter. Shall I give the ripple counter? Module. Module is ripple 4-bit counter. Let me write like this. Ripple 4-bit counter. And what are the inputs and outputs to this? Q is the output. Clock is the input. Then clear is the one more input. Need to understand. Then here I need to do the declaration. What are the inputs? Clock and clear. Clock, comma, clear. Then what are the outputs? How many bits we need to design? 4-bit counter means 3 down to 0. This is a Q. Then what I need to do? What I need to do? Now we need to instantiate, correct? Instantiate the T flip-flop. So let us write a T flip-flop. Let us make flip-flop 1 or flip-flop 0. Now what I need to do? Look at this diagram. First T flip-flop what? Q naught. What are the input is? Clock and the clear. Correct? First Q naught means what? Q of 0. Or the output. Followed by what? Input. What are the input is? Clock and the clear. Correct? Clock, comma, clear. This is the first one. Again, I need to instantiate the T flip-flop. Shall I make, this is flip-flop 1 of, what are the output is? Q of 1. Comma, is it clock? What is the input of this clock? Input of this is nothing but Q of 0. Correct? This is Q of 0. Correct? Q of 0. Then what? One more input is clear. Did you understand? Next, what I need to do? T flip-flop instantiation. This is nothing but what? Flip-flop 2 of Q of 2. Q of 2, comma, Q of 1. Correct? Q of 1, comma, clear. Then T flip-flop 3, correct? Q of 3, comma, Q of 2, comma, clear. Clear. Now we are done with what? 4-bit repeat. Now what I need to do? In the model. So, in the model. Now let us check for what? Syntax errors. Now we have model. This is nothing but data flow modeling of what? 4-bit ripple or asynchronous count. Did you understand? Now we need to write the design test bench to this. So what is the test bench to this? Shall I bring this up? Shall I use the same test bench so that I will modify the same? Okay. Now can you tell me what is the test bench to this? So module TB, what are the inputs are here? Clock and clear. Output is, now this is 3 down to 0, correct? Then connection. What connection I have to do is, first is Q. Let us, if I am going with this also fine, right? Because I am doing what? Connection by name. If I am putting any order also, it is fine. Correct? So clock is there, clear is there, what? Q is there. Then what I need to do? I need to monitor clock, clear, then Q. Same thing I can use, correct? Here what I need to do? Clock generation, this is for the clock generation. And this is clock is equal to 0, clear is equal to 1. So after this I am making what? Hash 15. And at this point I am making what? Clear is equal to 0. When clear is equal to 0 only, it has to do what? Counting operation. Ripple counting. Q follows the what? D, whenever what? Clear is equal to 0. When clear is equal to 1, Q is always 0. So I think this test bench is fine. So let us do one thing. I'm making, let me make this as increase the time of the clear 0. When clear is 0 only, it is doing the counting operation. So let me make up to 75, clear is equal to 0, 15 to 75. When at 75, I am making 1, clear is equal to 1. Now let us run this. Now let us print a Q in D, means decimal, counting operation. There is a syntax error here. Let us remove this. So T flip-flop expect 1 bit, got 4 bit. Let us check this program. Is it working fine when clear is equal to 1, Q is equal to 0? When clear is equal to 0, is toggling. Okay, the mistake what I have done here, what I need to instantiate here? Ripple counter, right? I need to instantiate ripple 4 count. Correct. Now let us run this code. Now here, now this is fine, but Q is taking as Q is printing the impedance since this is declaring as a white data type. Okay,
Same
can you
instantiation
debug it?
problem, sir.
Again,
Like,
instantiation is wrong.
Yeah, same like.
This is Q lock and here, but I'm using what this is nothing but I'm doing
We are
the
the
code by-
instantiation from the Ripple 4-bit T flip-flop, right?
Yes, yes.
So that is a mistake. F0, F1, F2, F3, you are instantiation. You give output post in that T flip-flop input is a post.
T flip flop. Okay, let us simulate T flip flop. Output and then followed by the input. Okay, let me check with the port connection by names. Okay, this is my T flip flop. What I need to do in this case here? This I should make what? Q. Q, comma, clock, comma, clear. Now I'm getting the counting operation. So what mistake is, let me repeat that mistake. What I have done is, in T, when I'm instantiating this, how I'm instantiating? Output, then inputs. But when I'm listing the ports here, when I'm listing the ports, I'm writing first inputs and then output. That was the mistake, sir. So that it is Q is not getting. So the value of Q will be declaring as a white data type here. You can see in the test bench white data type. So that it is default value of the Q white data type is nothing but one Z. I'm printing the Z. That was a mistake happened in the program. Okay. Now you can see when clear is equal to 0, it is doing the counting operation. Up here it is counting operation. Once clear becomes 1, what happens? Q becomes 0. Did you understand? 4-bit counter means how many count it should do? 0 to 15. After 15 means F. 0 to F. Hexadecimal print. After F again what it has to do? 0, 1, 2, 3, 4, 5, so on. Okay. So let me make, this is 500, finish time. Let me make this is 400. Up to 400, my clear is equal to what? 0. And then,
अबे दूध क्या चढ़ा है?
after 400, it should be what? After 400,
मम्मी
it should
दूध
be
है
my
क्या?
clear should be what? 1. When this clear is equal to 1, then Q is nothing but what? 0. Now you can see this is my counter 0, 1, 2, 3. So why I'm getting 1, 1, 2, 2, 3, 3 like this? Because it is a negative edge technique flip flop. If changes happen at the negative edge, then it will still remain same what? Same in the until the next negative edge comes. Correct. So this changes happening at what edge? When clock is changing from 1 to 0 means what? This is a negative edge. Now this remains changes to 1. Counting operation. Again this is changing at what? Again clock is changing from what? 1 to 0. Did you understand this program? So this is a counter. See 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 4-bit counter. After 15 what it should happen? 0, 1, 2, 3, so on. Did you understand? Are you able to understand what we are doing? Okay. Now let us run this in the models. copy this. Let us make a folder. Ripple count. Ripple count. Let me open the text file. So I'm going to copy the design file first. I'll be saving this as ripple.v file. This is a dot extension is .v file. I'll save this. It has close. It has open. And then now I am going to copy the one test bench. Copy. Copy this. Let's copy this program. So what first line I need to do, it is copied many times. Press remove all, delete all, control delete. Keep it at the first line. Now what I need to do? I need to include the design file. Include what is design file name I have given is ripple.v file. Okay, let us save as db.v extension. All files save. Now I need to copy the run.do file. Let's open this. Let's copy the run.do file here. Then file, save as run.do, save type as R file. Now this is my ripple counter. So design file, do that file, then test bench. Now let us open the model. So here I was opened the one model. Let me close this. Now this is a ripple counter. I'm going to run this command. So I'm using the dollar symbol monitor. It monitors the output, and this is my timing diagram. Okay. So let us zoom this. You can see this the counting is happening here. Let us keep the cursor here. So this is a negative edge. Up to here my clear is equal to 1. You can see this is my clear is equal to 1, Q is equal to 0. Whenever clear goes low means counting should start. Now 0, again this is 1. So up to here it is 1. Up to here it is 0. Whenever negative edge comes, this becomes 1. It will stay remains 1 until the 1. Next edge, again toggles here, all the flip-flop toggles. Again it becomes 2, 3. Now you can change this Q into the radix format of hexadecimal. Now 0, 1, 2, 3, 4. Again, let us zoom out. 6, 7. Up to F. After F, what will happen? Again 0, 4, so on. So this is working as a 4-bit one. Ripple counter. So how we are basically modeling this. Analyze this program. How basically we are designing. What is the program I was asking you to do? I was asking you to do the 4-bit ripple counter. To do this, first I was asking you to do the D flip-flop. Use the D flip-flop to design the what? T flip-flop. Use the T flip-flop means toggling operation. Use this toggling operation to model the what? 4-bit ripple counter. Now we are model the asynchronous counter, ripple counter. Did you understand this program? Huh? So let us copy this program. So let me copy the design file first. Now I'm going to ask you to do synchronous counter. Will you do that? So this is the program to this. This is my test bench. I hope this is clear. You practice once, okay? Any questions, any doubts are there, let me know. I'll clarify. I think that you are understanding how to do ripple count. Okay? Now let us go with the next question. Can you do this? The next question is to copy this question. Last question. Okay, you can copy this synchronous count. So just now we saw that how to model the asynchronous counter, ripple count. Now you copy this. The synchronous counter can be designed by using master-slave flip-flop. Design a 4-bit synchronous counter. Circuit diagram for synchronous counter and JK flip-flop are given below. In the next slide, I'll show that. Okay, the clear signal is active low. The data gets latched on the positive edge of the clock, and output of the flip-flop appears on the negative edge of the clock. Counting is disabled when the count enabled signal is low. Write the data flow description for the synchronous counter. Write the stimulus file. Stimulus file means what? Test bench. Write the stimulus file that exercise the clear and the count enable. Display the output count Q 3 down to 0. Output count 3 down to 0 means what? 4 bit. Okay. First you copy this problem.
आ गया फोन तेरा में